Good afternoon, everyone, and welcome to the Tide Seminar Series for today. And my name is Wenhua Zhao, and I'm very glad to introduce our speaker today, Tang from Oxford University. And Tim is Schmidt AI postdoc fellowship at the University of Oxford, and the Schmidt kind of AI theme is a very prestigious kind of activities in University of Oxford, which they selected 10 early careers to across the whole university to work on the adopting the machine learning or AI technology to engineering problem, which kind of lands quite well with the Tide Research Hub. And TMC, he got the PhD from University of Oxford last March, working on the extreme waves. And during the PhD, team developed various machine learning models, analyzing data from the lab, numerical simulations, and also from the method from the field. And team's research focus has been on the data-driven predictions for extreme waves and wave loading on offshore structures, and also interested in nonlinear physics on offshore hydrodynamics. So today, Tim gonna talk about the data-driven model, and I will hand it over to Tim.
Thanks, Wenhua. That's a really nice introduction. And so as Wenhua mentioned, I'm Tim from Oxford, and I'm currently at AI doing some data-driven and artificial intelligence work in line with fluid mechanics. And today I'm going to present is my previous postdoc work that got with Paul, and all our collaborators have been shown here, and we do get some quite pretty logo there, which the little bird is actually proposed by Paul, and the logo of our Sea Swallows project. Well, in terms of what is Sea Swallow standards, you will be able to know that later. And the research is being funded by EPSRC, and it's a collaboration between like University of Bath and Strathclyde and obviously Oxford here. I would also like to introduce all my collaborators. Howie, he's from Bath, and David Sai he's actually from Strathclyde, and he's really helpful with all the experiments. Dr. Xi, he's actually working on machine learning side, which gives us quite a lot of help. And obviously Paul Taylor, well, you probably all know him quite well. He gets lots of brilliant ideas and really guides the project through. And also two PIs from the project, Professor Jung Zhang and my supervisor, Professor Tom Adcock. So in today's talk, it's actually been composed of two separate talks, which is all about wave loadings on vertical cylinder. But the two different topics, one is on how we would actually try to build an engineering tool to predict these higher order forces on these vertical cylinders. And the other thing is that how we can design our experiment, like in the future, to improve the model predictions. So there will be two parts, and but the overall objective is quite aligned, which is we do worry about these severe wave loads or during the storm on these offshore monopiles. And because we are trying to build these offshore winds in a much deeper water with larger diameter, so these loadings, these hydrodynamic loading becomes more and more important. And the entire project, as we see Sea Swallows, is really talking about severe storm wave loads on the offshore wind turbines. Well, for this type of problem, it's actually quite established problem because if you think of that, we do get a Morrison equation being like raised about probably several decades ago. And well, the Morrison equation says quite straightforwardly, if we consider some form of regular wave, we can just calculate the force introduced by that regular wave on a vertical cylinder through a few coefficients there. Well, one is the tangent kd, which is depth correction, and cm is the inertial loading coefficient, etc. So it's actually straightforward. That takes one line to code it up. But then the problem is actually the Morrison equation provides our accurate estimations of the force actually we measured down in the tank. So here on the left-hand side, the blue line is actually the linear force. Well, we basically just build up a virtual cylinder, a real cylinder down in the tank, and we generate some waves, and we measure the force, the total inline force on that cylinder. Well, you need to mention that currently we focus on the unidirectional waves. And the red line here is actually what we measured. Well, if you compare to the blue line, which is what Morrison equation would predict, that's not really close. We do miss out the crest as well as the trough quite a lot. Well, both are really important for the extreme loading analysis and extreme value analysis as well. So in today's presentation, we were talking about something that could actually get us into higher order forces, which is what we call Stokes type of force model. The idea is really straightforward, is that if we can get our linear force model, which is exactly the blue line on the left-hand panel, and if we can follow the equation that on the Stokes type of force model on the left-hand side corner, now we will be able to obtain the second order force time series. And the nice idea behind the Stokes type force model is that this can be linearly superposition. With that being said, we could just add them together. And if we compare the plots we got on the left-hand side, now we have our linear force series as well as second order force series on the left-hand panel. When compared to the linear force series only on the right-hand side panel, we can see that our agreement is much better being proved. And it's also what's important to saying that is the second order time series, and you probably see here, on the panel, the frequency is doubled when compared to the linear frequency. And because all the offshore structure that's really being designed in the open ocean, we do want to avoid the natural frequency to be overlapping with the incoming wave. However, the natural frequency usually still for offshore monopile foundations or the wind turbines is still 2 to 3 FP here, which means these second order forces will be really important when you design a fixed offshore wind, because they will actually resonate with the natural frequency of the wind turbine, and hence kicking a lot of fatigue damage as well as contributing to the ultimate load. Well, because if you look at the left bottom corner here, the Stokes type force model can be expanded to quite high orders. So that's the reason why not we actually include all these higher order force time series. And then if we add them all together, what we get is on the left-hand side panel, which we do agree pretty well with the measured force. So that actually gives us a quite smart idea of how we would be able to predict all these nonlinear force loadings based on our linear input. Well, the linear input can either be a surface erosion input, because we can convert it through the Morrison equation, but it can also be the linear force input. So the idea behind the entire prediction tool or engineering predictive tool is that, well, we got our linear forces, and if we would be able to get all the force amplitude as well as the phase coefficient, because each nonlinear term is actually being categorized by an amplitude coefficient as well as the phase coefficient. So if we will be able to get all these coefficients out towards like fifth order, which we sort of believe that's sufficient for an engineering type of model, and the type of force model actually will tell us how big these like higher order force will be, and their phases information depending on these two coefficients. And now, if we add all them together, we'll be able to recover or predict our nonlinear force quite straightforwardly. But the only problem we got with our Stokes type force model is that we don't know this coefficient. And this coefficient is unfortunately being like varying with different parameters. The first one is Kr value, which is the cylinder radius. So that tells us how big a cylinder is when compared to the incoming wave field. The Kd here is actually the water depth. So that because, well, finite water depth will enhance some nonlinear interactions. And the last one, Ka, probably you will also be quite familiar with, which is wave stiffness. It's a quite classic measure of the nonlinearity of the wave. Well, in order to really get these coefficients out, we have to do some experiment or numerical simulations. Luckily, we do got plenty of experiment what's going on before our C-Swirl project, as well as we also conduct several new experiments here at the bottom shown in the background with gray. As you can see here, we do get quite a lot of experiments. And these are looking at different combinations of Kr, Kp, and Kd that they talked about. But the only problem with these measurements or experimental data is that what we get is already the nonlinear forces, right? So with that being said, we would actually need to isolate or separate all the nonlinear force we get from our measurement into different higher order harmonic forces. Well, this has been done in terms of the four-phase decomposition method. I believe that basically most of guys here had really been looked at before. And so I will probably skip a little bit that, but basically is that if we need to get the high order force components out, we have to repeat our experiment 4 times or 2 times. And the repeat of the experiment has a phase angle shift from 0 degree to 90 degree to 180. Basically, that's flipping the entire signal upside down as well as 270 degree. And by really linear superposition these forces, as you can see on the left bottom panel there, well, we will be able to extract all these nonlinear forces out. And because the first order and the fifth order are actually in the same signal time series, so that we just need to do a quite straightforwardly filtering, because, well, the first order signal and the fifth order signal, they are really separated apart in the frequency domain. Well, that's actually a quite neat idea, but there's more things to do, right? Now we collect all the experimental data, we kind of separate it into all these higher order force harmonics, but we still need to get all the coefficients out. Well, this is where kind of data-driven method would actually help a bit, because, well, we can use the linear least square method, which been previously used by the previous experiment, but now we actually reprocess all these data and with some nonlinear fitting methods, which is quite straightforwardly, but we can further enhance that by really looking at, so that is what the fitting method has been improved. Well, the blue line here is the exact force coefficient or the force time histories from second order to the fifth order here with the traditional method, which is linear square fitting. Which is being shown in the red, and the yellow one is actually the one with nonlinear fitting method. We do recover the third order in particular slightly better than the linearly square method, but yes, and also we get slightly better predictions or extractions of the coefficients at the second order as well. So with the nonlinear fitting method, we would now be able to actually get all these force coefficients as well as the phase coefficient. But the other thing we could do with the state-of-the-art like data-driven methods is that because what we do really want to recover is the total force. Then with that being said, we could actually use some optimization codes. Say currently what I'm using here is the gradient descent, and the idea is that how do we like fine-tuning all these combinations of all the coefficients and now make sure that it predicts the nonlinear force better. Because previously, or in previous studies, all these extraction of coefficients are independent. That means, well, if you want to get the second order coefficient, you only know the second order terms, and that's how you get second order coefficient. But now we were able to combine all these high order coefficients together and do another round of optimization, which actually proved quite a bit in terms of the accuracy on the total nonlinear forces. As you can see, that's just a demonstration of one case here. The blue line, so the y-axis is the forces, the x-axis is time histories, and the blue line here is what we measured down in the tank. The red one, the red dash, is that one without optimization. And after optimization, that being shown in the yellow line, well, we do get slightly better results. And that's just a quite classic machine learning type of prediction or demonstration of the efficiency. Well, on the right-hand side, that's the case with the optimization, and we do see a slightly reduction in the relative error in the maximum force crest, which is one important criteria for the design. So that's just the case so far, and then what we do is that we kind of plotting out all the phase coefficients from all the data what we got so far. It's unfortunately a bit messy here, but as we can see that we do see that for the signal, say for the second order coefficient, which is on the top line here, they do vary quite a lot with the Kr value as well as the Kd value, which is in the second and third column here. But for the Ka, which is wave steepness, because we are using John-Gross normalization, it's actually not varying too much for the same Ka and Kr cases. Well, we do see quite a lot of scattering on the third order. Unfortunately, that's also been shown previously from the extractions of the forces. If we can go backward, as you can see, the third order, we do believe that there might be some extra physics going on, or physical process going on there. So that's the reason why our model is not fully captured the entire third order nonlinear forces. So, with that being said, we got all the coefficients, and now that's where the machine learning comes to be applied. Well, the idea is quite straightforward. We've been kind of going through how we can use the phase decomposition method to get the force coefficients from the experiments or from the numerical simulations. Then we basically feed them into a Stokes type of GP model, well, Gaussian process model, and once it's been trained, then we can just feed in some nonlinear force or wave time series as the inputs. Then we will be able to get to the nonlinear force output on the higher order harmonic quite straightforwardly on the right-hand side. So there's nothing really tricky about the machine learning process here. well, we just feed in a bunch of coefficients, the entire model being trained on these coefficients, and the model will be able to predict that afterwards. Well, if we do look at some results in terms of the predictions, first we are going to look at is the wave group predictions. Well, it's a focused new wave, which I guess you will always be very familiar with. On the left-hand side, these are actually the total force. So on the y-axis, these are total force on the cylinder, and on the x-axis here is the time series or time vector. Well, our prediction model does agree pretty well, apart we miss slightly at the trough of the force, but basically apart from, and we can also see everything on the breakdown of each order of higher harmonics. Well, we recovered the second order, the fourth order, and fifth order quite spot on. So ideally, the yellow line does agree with the blue line pretty well, but the only thing is that the yellow line does not agree that well on the third order, which we already know that there might be some like extra physical process going on there. So we could also implement the entire thing to the random wave predictions, although there might be some tricks needed to chop down the entire time series into wave groups, but the entire logic behind these still holds on. So as you can see here, the yellow line here again is our model predictions. The blue line here is what we measured down in the tank. The difference is quite small as shown on the bottom panel. And if we look at the force exceedance plot, as we can see here, we do get plenty of nonlinearities when compared to the Rayleigh distribution from our force time results. But then our Stokes GP model can quite accurately predict all these nonlinearities or the higher order forces to the crest force amplitude here, which is quite nice. The other thing we would really want to do is, because what we are actually developing here is an engineering tool, and we do want to know where or when our model actually breaks down. So that's the reason why what I've been implemented here is called up-bounded confidence bound policy, which is based on a k-fold cross-validation procedure. And in theory, it will predict, it will give the non-cross criteria for the force predictions. Basically is that in reality or for engineering practice, no force should really be exceeding what the purple line really predict. And if we really put here down into the practice, well, that's really what we see. The purple line does cover the most of the predictions, almost all the predictions for our experimental cases, and that's providing a quite nice engineering tool that with like built-in reliability goes on. Oops. Well, in terms of the conclusion for the part one, basically we are trying to develop an engineering tool for predicting the higher order force harmonics based on the linear signals, and we will be able to do that based on the Stokes type theory within it, like data and like a data interpolation of machine learning. And the idea is that the entire model is working pretty well with the wave group results, as well as we can extend it to random time series, which is quite nice. And well, the advantage of current work is quite obvious. We don't need any kinematic results from like if you want to use Rayleigh or other force models, and it's relatively straightforward and fast when we do the engineering type of calculations. Well, in terms of future work, we do need to consider some of the breaking stuff which really hadn't been considered in our talk, really, in our model, really. So that basically concludes the first part of the presentation, which is, well, we try to build an engineering model. But the the engineering model we built here can really be improved by doing more experiments. And now our question is, say, if we're going to design a new type of experiment, right, down in the tank, how do we choose our parameters to get a better representation or have the most effective improvement on our model prediction results? So that's what we really about. That's what the second part really about. Well, we are focused on the model test cases. These are quite expensive. Well, that's also being applicable to like OpenFOAM or some CFD simulations. That's also computationally very expensive. And the idea is that can we incorporate some field data and as well as some previous test results to design our new experiments? And well, our case study here is really looking at wave loads on a vertical cylinder. The right-hand side bit, well, I'll probably not really go through, but I just need to stress about that is what we really care is the force amplitude coefficient. And that's really depending on three parameters: cylinder radius, water depth, as well as wave stiffness. Okay, so how do we design an experiment? Ideally, now what I've been putting here is all the previous experimental results. That's been put down in terms of three panels because ideally we have three parameters. So for the first panel, the cylinder radius is on the y-axis and the x-axis is really the wave stiffness. The second one is a combination of the water depth as well as stiffness, and the third one is a combination of water depth as well as the cylinder radius. The idea is because it's a three-dimensional space, I just get 3 plots. So how do we design an experiment? Well, ideally, firstly, we would like to repeat some previous critical experimental cases because all these cases are really sourced from different sets of experiments. They might not agree well with each other. So ideally, we would like to place more experiment to check out which set of experiment was not that accurate. And the other thing we would like to check out is that we need to provide a much better coverage of the entire space because we do see quite a lot of black space here that ideally we don't know what the coefficients look like there. So we need to do more experiments. And the other thing is really important is what's going on in the ocean. Well, if we just ask machine learning what will be the next best design, machine learning will give us an infinite large number because obviously the very large KRs will never really exist in the ocean. And that's the reason why we do need to look at these ocean data, which we adapt from the ECDMF hourly data. And what we do is we extracted all the information from 38 UK offshore wind farms from like 20 years. So for each wind farms, what we ideally extracted out is the significant wave height. Well, that's quite straightforward. The other one is the H max that tells us the hourly maximum wave height there, and as well as the peak period, which is measurement of how the wavelength of these waves. Paul does mention that peak period wasn't really a nice parameter, but I sort of, when I trained the model, that's what I picked. So next time I'll probably do it better. But on the other hand, if we do look at how does this sea state analysis being performed, I've been plotting out the Bing plot here, exactly on the same 3 panels. So the dark bluish show that these combinations are more happening frequently in the middle of the ocean. And for any design of such experiment, because we really put a cylinder in the middle of the tank, and the first thing we really need to decide is how big our cylinder will be, and that's critical because you can't really like change the size of the cylinder during experiment, because changing it will take a day, which is not an ideal utilization of the facility. So the idea is straightforward, and we do know that there is quite a lot of stripes here on the third panel, which is really because it's the water depth being plotted by the cylinder radius, and both are actually fixed. So we can see all the experimental cases must be done in a straight line, that if we don't really change the water depth here. And now the question is how we could design our experiment. What I've been taken, the approach here is called information acquisition function, which is a Bayesian type of sampling idea, which on the left-hand side of the equation you see here, which is our next best sample point. By means is which our parameter combination we should use to do our next set of experiment. And the middle bit is really about the model predictions. There are two types of things need to consider. The first one is the model prediction residuals. Well, that's quite straightforward. That's our model error, right? If we got a very large error, the model prediction error there, we might need to check out whether it's our model goes wrong or there might be some uncertainties when we do the experiments. The second one is model prediction uncertainty. That's also a very standard parameter, because that tells us how confident these our model predictions are. And well, if we got a far less sample or very coarse sampling in certain area, the model will give us a quite large confidence interval, so that we know we need to place our next sampling close to that point. The last bit is everything is really being bounded by the C-state analysis, means that what we are going to test out in the tank should be something that really can happen in the open ocean, right? So that's the reason why there are the conditional statistics being put out at the very bottom. And with all this information available, and we got our information acquisition function, now we will be able to answer the question, what is the most representative cylinder radius we could use in our experiments? So before we would be able to answer that, the first thing we would really need to know is how the machine learning actually make our decisions, right? How machine learning would believe that why we should place our next parameter here or there. So what we're going to look at here is the slices in the information acquisition function, which we just showed before. The idea is the larger the value is showing on the plot, which is more yellowish, show that machine learning said that there is more likelihood that you should place the next experiment there, or the machine learning said that these are the importance criteria. So now we're looking at 3 slices into different KD values. And what we do first see that machine learning does not really like very steep cases. Up until 0.2 Ka values, machine learning shows almost no interest at all. That's partially because, well, in reality, it's really unlikely to get a very big waves in the open ocean, which is also problematic because some of the design really need to design towards these very rare but important criteria of big waves. The other thing is machine learning automatically also rejects almost all the small low KD values, low steepness values. Well, that's true because for low steepness cases, there isn't much nonlinear interactions going on. Nonlinear physics isn't really pronounced in that region. So, well, we basically Morrison equation can do a fairly good job. And the other thing which is quite interesting is that we do see a shift from very shallow water cases from KD 2.89 to relatively deep water cases, which KD is equal to 2.3-ish. So that's quite interesting because, well, that definitely shows that our trained machine learning model tentative to understand some physics or some real cases going on. It's because if you think of all the wind farms, when you're trying to build a wind farm like in the deep ocean, right? So deeper water side, these wind farms are usually being associated with a larger diameter in the monopile. So that's the reason why machine learning sort of automatically also consider this trend. The other very interesting trend machine learning does give us is that, well, there's a very strong shift from like KD to 0.89 to intermediate water depth. So from shallow water depth to intermediate water depth, the shift is quite significant. But then the shift from the intermediate to the deep water is actually quite minor. So that basically tells us that, well, the nonlinear physics that's going on from the shallow water to intermediate water depth, there's lots of things actually going on, and you need to shift that. But then the asymptotic behavior of the deep water forces basically tells us that, well, you won't see lots of interesting change between the intermediate water depth to on the deep water side. Well, with that being all said, we can finally try to design our experiment with the first parameter, which is what's the most representative cylinder radius. If we integrated the information acquisition function along the line of different R value or the radius values, that's a line what we got. And we do get a local maximum at 0.3 meters ish, so that we know that the most optimal design of our cylinder sizes will be about 0.3. But unfortunately, that's not possible in the Kelvin tank because the width of the tank is about 5 meters-ish. So if we place almost like 0.6 meter in diameter of cylinder, that basically blocks up too much fluid. And that might cause some like blockage issues. So that's the reason why we tend, in the end, we go with a radius, cylinder radius as much as big we can get in that tank, because that's a monotonic increase towards the 0.3. And we finally settled down with 0.2 meters there in terms of the cylinder radius. And all these small dots, the star dots here is a new experiment actually being suggested by the machine learning by sampling the information acquisition function. Well, that's quite straightforward. And now we actually not only collect these parameters, we actually go down the tank and doing all these parameters. And now we will be able to compare by a classic grid search method. So we basically place our dot manually, or we can use some machine learning method to guide our design. So on the right-hand side, so on the bottom panel, y-axis here, what we got is the relative error. Well, that's just quite classic measuring the model performance. And on the x-axis here is number of new samples. Well, we do see that if we do more experiments, our model prediction will be improved. Well, that's for sure, because for machine learning method, at certain range, the better, the more data you intake, the better performance you'll be. But then the second thing we're quite interested in notice that is if we follow the experimental cases designed by machine learning methods, it's actually like converge or reduce error much faster than the one we did manually or we designed manually. And if we look at the prediction difference in terms of one that with the grid search method, which in the purple dots line, and the one that is with the yellow line, which is the Bayesian sampled method. So basically, we ask machine learning to design our experiment. We do see that the purple line, the yellow line does slightly better. So that basically confirms what we see on the left-hand side, that if we follow the design from the machine learning suggested cases, we can actually get a slightly better results. So In conclusion to my second part, the idea is straightforward. We ask machine learning, so what type of experiment we should do and what type of parameters we should do. And then we actually do these experiments being suggested by the machine learning method. And then we do see quite a significant improvement in terms of the accuracy, model accuracy, but we also see quite a lot of limitations. The first one is obviously, if there's no constraint on the cylinder radius, machine learning will suggest that you should change cylinder radius every time you do a case, which is certainly not possible. So, machine learning didn't notice that changing a cylinder size would be quite a lot of effort doing the experiment. The other thing is that, water depth cannot be changed during the entire campaign, unfortunately, following the same reason, because pumping the water out and get the water back in and recalibrate your wavemaker, that takes just too much time. But, and the other thing is, I've also mentioned that our current case is really just focused on the nominal cases, so day-to-day wave conditions, which does not have any focus on the extreme values, which can be incorporated really in the later research. But we do have quite a lot of advantages. The first one is that machine learning allows us to incorporate all the field data into our experimental design, which, it's slightly more trickier when you follow the industry type of stuff, and you need to put much more effort into that. And the second thing is that because the information acquisition function is really user-defined, so that you'll be able to tailor it to your need quite easily. And if you want to say focus on the extreme cases, that's also quite straightforward. And finally, these machine learning methods, if we really look at the information acquisition function, we do see that this machine learning method takes some of the fixed insights into its predictions, and it is actually written, and so it's actually showed out in the information acquisition functions. I guess that's probably toward the end of my presentation. Thank you guys for listening, and if there's any questions, I'm more than happy to answer. Thank you.
Thank you very much, Tim. That was an amazing talk. Anyone would like to ask questions? I know we have a lot of PhD students working with similar techniques, so all right, I'll start. Oh, did you want to ask something, Christy? No. Tim, I think maybe I missed something at the beginning. I didn't quite follow why in a sort of Stokes type model, one of your parameters was Ka. Maybe you could.
Actually, we found out that Ka wasn't a very critical parameter when you think of the Stokes type model, because if you follow the John-Groove forced non-dimensionalization, everything should be really focused or be really a straight line in all the K values. But on the other hand, the design of the machine learning model is that if we don't believe that's a totally non-physical behavior, if we feed in more data to that, or we give it more insights into the model, ideally it should perform better. From the theory itself, unless I guess for very large Ka or very large Kr values, which inviolating the slender cylinder approximation, there might be some correlation with Kas. But on the other hand, yes, we do find that it's quite a straight line with Ka value. But on the other hand, machine learning can still predict a straight line. So that's not being a real problem here.
Great, thanks.
Hi, Tim. Really interesting talk. I'm wondering for the first part, how much training did you have to provide the model to achieve the results that you had?
So we can have a quick flashback to the, that would take a bit of time, but if we flash back to almost, So the table there, you will see that that's about 100-ish cases. So that's not a big amount of bulk of data. The idea is that those type of like the Gaussian process model is already a quite good model that has its generalization ability to be like fairly established for very small linear data. The other thing is that the Stokes model that we introduced basically simplifies everything. If you just put like 4 time series thing and you want another time series result, that would be very demanding for models, and that couldn't really be achieved with such a limited amount of data. But because now we are really putting like 3 parameters and asking 1, so the entire mapping between the 3 parameters and our like final amplitude coefficient wasn't that tricky.
Yeah.
So that's the reason why incorporating some physics in your machine learning model will be really helpful. And then to be honest, our machine learning model here is just really using as a like fancy way of data fitting.
Yeah, and that I guess that answers the second part of my question, which the training data is an ensemble of all the experiments together, right?
Yes.
Yeah. Okay. Yeah.
Obviously you couldn't really use the all data, otherwise you don't have any test data.
Sure, but
yeah. So
yeah, select ones of each experiment group. Yeah.
Yeah, but the entire database with attributes from all these data sets we collect from previous experiments and what we do in our new set of experiments.
Thank you.
Thank you.
Any more questions?
Have you tried any deep learning method to test the coefficient?
Yeah, I mean, deep learning method is certainly a very nice tool, but given that you have sufficient data, our data here is unfortunately, the getting data is very expensive. Either you need to do experiment, or you really need to do some like CFD simulations, and you have to trust your CFD simulations as well. So, basically on that cases, I've sort of tried some deep learning method, but that requires a huge amount of data to be trained and properly performed. I reckon that the performance would be probably better if the model being fully trained with deep neural networks, but we just don't have such a lot of training data available here.
I got one more question.
Okay, yes.
Yeah, I'm just curious. I mean, for this kind of machine learning method to predict this kind of things quite new for me. And you also mentioned that this currently is all based on the normal case, such as non-breaking case is quite small, but you also mentioned that maybe you could apply this kind of method to some extreme cases, such as K goes higher and gets breaking.
Yep.
I'm not quite sure. Maybe you need to answer. How do you feel about that? Is that promising for this kind of extreme cases, or possibility of the kind of machine learning method to that cases in the future? I think.
Oh, okay. So, in terms of machine learning for this specific case to predict extreme values, there are quite a lot of ways you can do that because the entire framework doesn't really limit it at anything you want to do. Firstly, feeding the C-state analysis with all the extreme values. So let's not focus on anything that is nominal on a day-to-day basis. That's a really straightforward one. But if you want to think of from machine learning side, that's also quite straightforward. If you look at the information acquisition function, that really is just a probability distribution, right? And thinking of how you can sample the extremes in a probability distribution, you just take the log, right? Because if you are thinking of 2 PDFs, right, they are really like if you just sample or measure the difference of these 2 PDFs in a like linear scale, you are actually measuring the dissimilarity in the bulk of the distribution, which is along the mean value. But if you just take a quite straightforwardly a log value, that's not, I'm saying you should do that, but that's one way you can do that. Then everything was focused on tail. because if you think of a log scale PDF or the CDF, right? So any difference towards here will be massively like enhanced, and any difference toward there, that's just a small value, so we don't care. But anything really focusing here will be magnified by the log values taken. So that's a quite straight way of how you could sample the extremes. Well, I guess there will be also many other methods, but that's just 2 ways in the top of my head. So.
Maybe I'll finish with one question, but it's a tricky one, I think. So you mentioned predicting the third order superharmonic forces has been difficult, and you suspect there's some unresolved physics or unknown physics. I mean, do you have any hunch or sort of understanding of what that might be?
That's actually a really good question. I mean, Paul can probably talk you through in terms of his insights, but for me, it's certainly something quite consistently being showed in previous experiments. And well, if you think of the FNV model, they do sort of also see like a quite large disagreement as the third order, although we probably be, well, one is really from like a potential flow theory framework-ish. But yeah, so we are not exactly sure, unfortunately, what's the underlying physics. Well, I've been listening to like Morling's idea of like third order interactions with like wave structure stuff. I'm not sure if we got a quite clear clue there. Yeah, Paul, I guess that's the answer.
If Boltonson and Nick Newman don't know, I don't see why we should be expected to know the answer. I mean, just on that, although you've not mentioned it, one of the studies we did previously, we also looked at the sixth harmonic, which is a double harmonic of the third. 1, 2, 4, 5, and 7 work very nicely. 3 doesn't work very well, neither does 6. So there is real stuff there that we don't understand. So watch this space. I have another really smart person looking at it. Maybe we can resolve it. I don't know. So.
Fantastic. Thank you very much again, Tim.
Thank you, guys.